Well, welcome everyone. My name is Artur Stefański. I'm a research fellow at the University of Minnesota in Forest Resources Department. I'm also a PhD student at the department. I'm also running a research project which we'll talk a little bit about today. So here we are today to visit a project which we have a funny name for. It's B4Warmed, and it stands for Boreal Forest Warming at Ecotone in Danger. Funny name, long name, and very confusing, but I think it gives away quite a bit of what is this project about. It took us probably about a week to come up with that name, which was pretty funny. The project started in 2008 upon initial call sent out to the researchers by Department of Energy, and their main request was to come up with some research ideas, research projects which will investigate pretty much any organism. They were willing to fund any organism. Why, if you would investigate it, the organism which lives at its range. And fortunately here at the University of Minnesota, and particularly here in Cloquet Forestry Center, we are in a very lucky spot because we are in the ecotone between two big biomes, between the temperate forest in the south of here and boreal forest north of here. For that reason, we are lucky, and we decided to ask one big question: who will do better in the future climate? Will that be boreal forest or will that be temperate forest? And because of that perfect location being on that ecotone, so in that edge between those big biomes, we have multiple species which either have a southern range or northern range. And because of that, we thought that those species will be the most sensitive in this range. That's why the perfect location, and that's why the Cloquet Forestry Center plays perfect role and perfect spot for setting up this research project. However, we set up two research sites, not one, but two. Not because we felt more challenged, but because the other side is located on the other side or other edge of that ecotone, and provide us with additional factor in our research and answering the questions which are related to the gradient of the climatic change. Because our other research site, which is located also on the property of the University of Minnesota in Ely, is not only 120 miles apart, but is also 2 degrees apart. And anything what I'll be talking today, it's in Celsius. So I apologize for not using imperial system here today. With that, I would like to welcome you, and let's go and see the site. All right, so here we are, and as you might notice, we're not only researching plant biology, but also physics, because we just teleported here from the gate. So anyway, we're here. We are in the middle of one of the research blocks. As you can see, some of the structures around us. Those are our research plots where we conduct our research. And to begin with, the design is multifactorial. One of the bigger factors are the different light conditions. So this group of plots, what you see here, is on previously clear-cutted old forest stand of mixed aspen and red pine and white pine, and that's where we have one group of plots because we want to address the questions which relate to regeneration in the clear cuts. But also we have a same group of plots located in the understory, which is behind me, where it's the exactly same setup, which will address the questions more related to the regeneration in the understory of existing stand. Now, so we have two sites. Now we have two light conditions, and on top of that we have 3 temperature levels or treatments. The one plot, for example, behind me, it's the highest level, and this is 4 degrees above the ambient. Then one plot, which we might see it, is to my left, is 2 degrees above the ambient, and one in front of me is ambient. Now you might ask yourself or ask me, why those 2 different temperatures, and why 2, why 4? The reason for those 2 temperatures is because we ran the climate models at the beginning of the project, and we, based on the predictions from 10 years ago, we decided, or we choose the dates which will potentially happen in the future in Minnesota, and specifically here in Cloquet, in about 50 to 75 years from now. So that indicates basically about the 2 degrees above the ambient and 4 degrees above the ambient. So you might ask why we choose those 2 different temperatures. We choose those 2 different temperatures because we ran the climatic models at the very beginning of the project, and we saw those projections, and we saw that in about 50 to 75 years from now, Minnesota, so as we're here, and those locations here will experience about 2 degrees and 4 degrees warmer temperature on average than we have it now. So that's why 2 and 4 degrees. So you might ask actually what other uniqueness this project might have. One of the biggest uniqueness of this project is that there is no chambers. As you can see behind me, we have infrared heaters, and I'll talk about this in a moment, which heat those plots inside, and in essence that tissue inside. The other uniqueness of this project is that we simultaneously heat above and below ground. So as you could imagine, underneath of this plot, so buried in the soil, there are warming cables. So you might have heard about other research projects where they were looking at the climate change and the effect of warming, but more often than less, lots of those projects either heated the soil or heated the above ground. Here we heated both, and we heated them without any chambers. So there is no greenhouse artifact, meaning that primarily changes in the relative humidity and vapor pressure deficit. So now you might wonder how all this system works. So first of all, in each of those plots, you can see a bunch of those sticks. Those sticks have temperature sensors attached to them. We have also a bunch of temperature probes sink in the soil, and they measure the temperature on each of the plot, above ground and below ground. All that measured temperature comes in to this white magic box, where we can see a bunch of wiring and cables and small tiny calculator size computers which controls all those plots. This computer here in this box collects the information from those sensors in those plots and then compares to the similar sensors on the ambient plots, and if the difference in temperature between those plots is at the right level or right differential, it sends the information to the heating elements, so the infrared heaters and below heating cables do not heat. When the difference is not at the right level, its differential is too small, the computer sends the information to the heaters, heat it up. And it also tells how much heat needs to be applied in a given 10-minute cycle in order to bring that heat to the right level. So now we know how the temperature is controlled on those plots, but how the heat is applied. So for the above ground, we have the infrared heaters. Those are the same type of heaters what, for example, farmers use to heat piglets. However, we adapt them here in the forest to use them to heat those plants what you see in front of us. And those heaters are getting signal from the data logger, as we learned just a minute ago, how much heat or how much power needs to be added into those heaters in order to bring that temperature differential to the right level. Similar situation happens with the heating cables, which are buried inside that plot. And for the comparison, and you can see on my background, there's the ambient plot, which we use as a control to which we compare the temperatures of this plot. So you have heard me talking about climate change and our interest in investigating the effect of the climate change, and I've been talking a lot about the temperature. However, there's other side to the climate change, which is precipitation. And as you might heard of, not only the temperature changes with the new climate, but also precipitation. In a lot of places, it has been predicted that there will be less rainfall, but also in lots of places it's been predicted that there won't be much change in the rainfall, or there will be actually increase in the in the rainfall. And particularly here for Minnesota, in the northern Minnesota, the prediction is that the rainfall will stay relatively at the same level, maybe even with slight increase. And you might ask, well, what kind of knowledge we want to know about it? Well, in a warmer world, there will be higher evapotranspirative demand imposed by the higher temperatures. Therefore, the plants will experience drier conditions because water cycle will be much faster due to that evapotranspirative demand. For that reason, we develop another factorial design with the rain removal. For that reason, we have a plots where we have ambient rain, where you don't see any structure on front of it. And we have a rain removal treatment, which is right behind me, where you can see that tall structure with that white bar. That's a rain out shelter. And we use those to remove about 40% of the rainfall to imitate the drought or put those plants in a condition so they experience some dry conditions which they might face in the future climate. So you might wonder how the rain out shelter works. And for that we have to have someone on call, and as you can see right there demonstrating, that person needs to come in here as shortly before the rainfall as possible and then manually unroll the shelter, cover up the plot, and so then when the rain comes in, it falls on the rain shelter, brings discharge away from the plot and effectively remove out of the plot. And after the rain, that someone, in this case Ryan, needs to come back and roll them back. So that's how we operate those rain shelters. So now, as you can see, teleportation still works. And you might be interested what we learned so far. We've been working here for 10 years. That's a pretty long time. And you would wonder like that we should learn something by now. Well, we tested, as I mentioned before, the ARC hypothesis, who will do better? It will be boreal forest or temperate forest. For that reason, we planted some representative trees, or would represent both biomes. So we have, for example, here jack pine, which represents boreal forest, or paper birch, which represents also boreal forest, or some oaks, which represents temperate forest. And we ask basic questions related to plant phenology, so how they change over the time, over the course of the season. We test some questions how they perform, so their physiology, and how well they respirate, or how well they assimilate the carbon. And also we look at the overall growth, so overall success of the plant, which is also defined by their survival. And for that reason, we learned over the 10 years of research that the temperature alone can extend the growing season roughly for about 2 weeks in the spring and 2 weeks in the fall, which gives a lot of advantage for those plants to assimilate carbon for a longer time, to potentially get more of it, grow better. So you might think, wow, the warming is actually probably pretty good for the plants. If they can have a longer growing season, they can assimilate more carbon, they can grow better. What else you would expect from the warming better than that? Well, the story is not that clear, because the water is the key here. And in the shoulders of the season, so in that spring and that fall, when we extending growing season through the warming, then the warming is beneficial because typically, at least here in Minnesota, the water is ample, either the snow melt or the fall rains. However, in the middle of season, especially in the drying period, like July and August, the time where you should be here actually, is the driest part of the season. And so during that time, the warming has a negative effect, to the point that actually anecdotally, I can tell you that during the hottest days in August, plants do not have a positive photosynthesis at all. Meaning that all they're experiencing is a fight for survival till the conditions will improve, meaning the fall rains will come in. So, as you can see, it's very important to look at the plant phenology. So when there's the period of time when they can acquire carbon and respirate, but also it's important to look at their physiology, basically to quantify how well they're performing in a given conditions, either in that beneficial spring and a fall, and that probably not so beneficial middle of the season. And then we can define this by overall success in survival and the growth. And what we learned about that? Well, we learned that plants which grow in native ranges south of here, so the temperate species, they do perform better in the warm plots. And the species which came from the north, so boreal species, they do perform worse. And that translates for the poorer survival for the boreal species on average, because all we're talking here is always average in science. So poorer survival for the boreal species and poorer overall growth. So the temperate species are definitely favored by limited water throughout our rainout shelters and through elevated temperatures. And I forgot to mention that we are very opportunistic researchers. And so for that reason, we decided to add another component, which probably you might not be too happy about it, because we decided to test the effect the climate might have, or the future weather, on the invasive species. So yes, you guessed it right. We planted here on purpose invasive species which were not here before and most likely will stay here forever. Although, truthfully speaking, the plan is to remove them. So, on top of the boreal species and temperate species, we also have invasive species, in particularly buckthorn, the common buckthorn and the glossy buckthorn and a couple honeysuckles. And our goal is to see how that manipulation of the rain and the temperature will affect their growth. And if by chance native species which are better adapted to those conditions, in this maybe particular case the temperate species which will fare much better in the future weather, will actually get competitive advantage over the invasive buckthorn, which has been introduced here. So we're looking at their responses as well, and especially from the perspective that one of the biggest characteristics which gives the good advantage for the invasive species to outcompete native ones is that they leaf out earlier. So their phenology is quite different than the phenology of native species. And as you remember, we've been talking about the advantage of the earlier season and the wet part of it. You might see that if the buckthorns are leafing out earlier and they can take advantage of that early growth season because of the warming, they might actually be even more competitive comparing to the native plants. And so we try to address those questions. I don't have much results to discuss yet about that because this is just ongoing part of the project, started in the last 3 years. So you'll have to come back to another NASP meeting. So here we are again. Now you might wonder what all that means, and you might think about anticipating your question, what will I can give you prescription for your forest? Well, I cannot give you one. I can only tell you what we learned so far, what is the basic biology, and you have to figure out on your own how to apply that knowledge, how to use this to your advantage. Knowing that, for example, as I mentioned, that oaks potentially will do better here, you might think about it, maybe introducing oaks rather than planting jack pine. However, it is your role to be a fortune teller, because a forester, you have to be like a fortune teller. You need to look in that crystal ball and you have to vision or see that forest in 100 years at the end of this rotation, at the end of a cycle, and then try to work towards your goal, towards your vision you saw in that crystal ball. And with that, you are the one you should interpret those results and come up with your own prescription for your own ideal forest at the end of rotation, what you envision in your crystal ball. So with that, I would like to say that was a lot of fun, even you guys were not present here. And I would like to say, if you're around, don't be a stranger, stop by or come back next year and see you around.